Hello, my name is Gerritse from the Netherlands, and I'm going to present my paper on graph-embedding empowered entity retrieval, which I did together with my supervisors Faegheh, Hasibi, and Arjen Vries. So, what are we going to tell you about? Let's break down the title of our paper. So first I'm going to tell you a bit about entities, and then I'm going to tell you about how we can use graph embeddings for that. And next, we're going to explain how we did entity retrieval with all of that. So first, let's recap what entities are. It's nice to all have the same definition for that in mind. So entities are can be everything, can be people or buildings or events like ECIR 2020. So if you want a very basic guideline, everything which you can find on Wikipedia can be considered an entity. And Wikipedia, we can consider it's a knowledge graph where all pages are connected to each other with links. So we have some extra information of neighboring pages which link to each other. And with entities, we can retrieve them just like normal document retrieval. So given a query, find a document and find an entity. However, entity retrieval is a little bit different than document retrieval because entities, like I said before, are stored in a knowledge graph, while documents are stored in a regular database. And then entities are more structured because you know the link and also the way the page is structured is often, we can find more structure with that. And also we know the relation between pages. So that brings us to our research questions. Can we add graph embeddings to entity retrieval models to improve them? And if we do that, which queries are helped the most by the graph embedding part? So how are we going to do the embeddings? I'm sure most of you are familiar with Word2Vec. So Word2Vec learns embeddings of words by trying to predict context of words according to a word. So here you see an example. And then the weight factor of the neural network we consider as the embeddings. So you see an example where you can change the middle word and then you can predict the context according to that. And we can, in Wikipedia to Vec by Yamada et al., this model was extended for Wikipedia. So here we have the normal skipgram-based model. So you can see that in the middle where we try to predict the context according to a word. But then we also do the same, but then instead of using words to words, we use entities to entities. So we try to predict the neighbors to an entity. So then you can predict entities to entities, but then you also need to link words and entities together, and we do that. They do that by the anchor text. So you have in the right, you can see the example Aristotle was a philosopher, and then Aristotle is the entity and was a philosopher is the anchor text around it. So then you can link the entities and the words together. So the loss function, so with normal Word2Vec, it's just the loss function of the words, but for Wikipedia to Vec, they combine the loss function of the words, the entities, and the anchor text. So we have embeddings of entities and words in the same vector space. This is the method we're going to use. How are we going to apply this? Our idea was to use entity linking. So suppose you have a query, for example, who is the daughter of Bill Clinton married to? Then we can use an entity linker like tag me to tag the entities in the query. So this tags the entity's daughter with a confidence score of 0.13, the entity of Bill Clinton with a confidence score of 0.66, and the entity married to it mistakenly links to same-sex marriage with a confidence score of 0.22. And we can use these tagged entities and the confidence score to compute a score, because the idea is that if entity is relevant to this query, the embeddings of the entities will also be close to the embeddings of the tagged entities in the query. So the relevant entities are Chelsea Clinton and Clinton family, and we suspect that these entities should be close to daughter Bill Clinton and same-sex marriage. How do we get a score out of this? So the score we compute is as follows. So we have an entity-based score, which takes an entity and a query. And then it sums over all the tagged entities, and then it computes the confidence score times a distance metric with entities. So if we take, for example, the entity Chelsea Clinton and the query who is the daughter of Bill Clinton married to, we get the score of 0.13 times the similarity of Chelsea Clinton and daughter, plus 0.66 times Chelsea Clinton and Bill Clinton, plus 0.21 times Chelsea Clinton and same-sex marriage. And we get a score out of that, and we will use that for ranking. Well, what are we going to use to do this ranking? For that, we used DBpedia Entity Collection version 2. So this is a collection of 476 entities and almost 50,000 query entity pairs relevance judgments. And there are 3 relevance judgments. So we have one for not relevant, relevant, or highly relevant. And there's a big range between the number of relevant entities. So we can have either all people named Jimmy, which have almost 1,400 relevant entities, or Spring Shoes Canada, which has only 1 relevant entity, and everything you can imagine in between. So we wanted to use Wikipedia embeddings on the DBpedia dataset. Now, DBpedia is derived from Wikipedia, but there are some differences. So DBpedia Entity Collection used 2015 Wikipedia, but we were not able to find the exact dump, so we used 2019 Wikipedia. And there's some mismatch going on, because you can imagine the world changes. Some entities change names, some are deleted, and there's some changes. However, luckily through the API of Wikipedia, we could fix a lot of those mismatches. And then what's also a problem was the default setting of Wikipedia to fact disregards entities which are either don't have a page which is long enough, or which don't have a lot of income or outcome links. So we had to play with the settings a little bit. And you can see that in the default settings, we had almost 10,000 missing entities. And then both with the API mismatch fixing and with changing the settings, we fixed it to only 1,000 missing entities in the QRL. So that's around 2% of entities in the QRLs, which we don't have. So here to highlight that again. So our experimental setup, which we did for this work, we had first train Wikipedia to fact, which I explained with the settings experiments we did before. And we did it on Wikipedia dump of 2019, and then we trained the embeddings. You get embeddings for almost 2 million words and 12 million entities. We trained 100-dimensional embeddings through limitations of our hardware, and it took 24 hours on our server. So to compute the scores, we are not going to rank everything. We're going to re-rank top 1,000 provided with other methods, which I'm going to tell you more about. And then we compute 2 scores. So with Wikipedia to fact embeddings, you can both take the graph component into account, which I told you before, but you can also not do that. So then you have context-based embeddings, which are actually just word embeddings, and then the context plus graph-based, which take both context of the word embeddings and the graph part into account. And we use the train test bit from provided by the Wikipedia Entity Collection, and then evaluate it on NCG at 10 and NCG at 100. So to combine the scores with the scores given, with the runs already provided, we're going to compute the linear combination between these 2 scores. So if the total score, which is the entity-based score, which I told you a few slides back about, and then also the score provided by FSCM or BM25, some the score which is already computed. So that's the one we're going to re-rank. And then we compute the lambda values of this, and you can see that of the ones with the graph part, so these are denoted with the G's underneath, the lambdas, so the importance of that part of the score is higher so than the ones without. So that's good to know. Then we know that the graph part actually helps the score. So next, I'm going to show you a big result table. I've blacked out a little bit. I hope it's clear. It's a fairly big table. So first, we're going to show the scores which we're going to re-rank. So these are FSDM and BM25. And these runs are taken from the DBpedia Entity Collection. So these are pre-computed runs. And you can here see the scores of that. And FSDM also has a score of the, also an entity-linked score, but this was done with a different method. So then first we're going to just re-rank the scores, so not the linear combination yet, but just the re-ranking. And then we see that if we just re-rank the scores of FSTM or BM25, the scores are worse than the original scores which you're trying to re-rank. However, if we do that linear combination, it becomes significantly better with two-sided t-test with alpha smaller than 0.05. And with the combination of BM25 and the graph part, we even get a state-of-the-art on this data set. So that's nice that the scores are higher, but we want to get a little bit more insight of why exactly it is higher, why it performs better. So that's where we're going to compare the graph part and the non-graph part. And we compute a few scores on this. So first we want to take into account the cluster coherence. So we know that documents relevant to the same query should cluster together. In this case, we actually have something, we have an embedding for every document because a document is an entity. So it's easy to compute cluster-based scores because we just have a numerical representation of all our documents. So first we're going to compute the cluster coherence score defined by Faegheh et al. So on the x-axis, you see all the entities, and then 0 is the entity with the most of the query with the most relevant entities. So that is a query with 1400 relevant entities. And then at 300, there's a query with only 10 relevant entities. So that's where we kept it off. And then the scores you see is the percentage of relevant entities closer to each other than a certain threshold. So in this case, that's 0.9. And there you can see that with the length graph part, the entities are clustered much better, so there's much more coherence with most of the queries. So next we have some other cluster scores which you compute. So we have the Davis-Bouldin score and the silhouette index. And with the Davis-Bouldin score, lower is better, and with the silhouette score closer to 1 is better. So with both of these scores also, the part with the link graph performs better than without the link graph. And then next we're going to take some queries with between 100 and 200 relevant entities and plot them in a lower dimensional space using UMAP. So here we have the UMAP plot with 12 queries with the graph structure. And you can see that for some queries, for example, the yellow part and the red part are D-Day normally in phases and fit no more effects. They're very close together. You can see the orange part and the purple part, which are both companies. They're also close together. So you can see a very clear structure of what you would expect of entities coming back in the structure of the embeddings. However, if we use the embeddings without the graph structure, you see that it's much more meshed together. There's a big overlap in the middle, so it's less clearly distinguishable. And we also wanted to look at a few false positives. So here the dots with a border around it are false positives. We do see, however, that the false positives land very closely in the clusters again. So that's unfortunate, but it's also very explainable. Because suppose we have the query South Korean girl groups, then we see that some of the false positives are Shiny, which is a South Korean boy band, and Hyuna, which is a South Korean female singer. And how they are not relevant to the query. However, in the embedding space, it's obvious that they're very closely related to South Korean girl groups. So they're similar in the embedding space, but not relevant to the entity. So that's very explainable. Now, next, we're going to look at what went better or worse when using the graph embedding related entities. So some things went very well. So one query which performed much better was, for example, which instruments did John Lennon play? And it gets linked to the entities John Lennon and musical instruments. And then one of the most similar entities to these two is the page John Lennon's musical instruments. So that's perfect. That's exactly what we want. But then sometimes things go wrong as well. And we looked at a few entities which performed worse when using the graph part. And sometimes they're wrongly tagged because of a spelling mistake. Sometimes the importance is given to the wrong entity score. So example, which I showed before with Bill Clinton, and then sometimes a high confidence can be given to an entity which is not really relevant to the sentence. And then sometimes entities are not embedded. Like I told you before, we did not have an embedding for like 2.7% of the entities. So yeah, if that's the only relevant entity, we cannot find it because we don't have an embedding for that. So with that, I'd like to conclude our work. So to conclude, the entity embeddings, specifically the graph part of the entity embeddings, improves entity retrieval. And entity embeddings also fit the cluster hypothesis. So if you compare the graph-related part to just the word part, the graph part confirms the cluster hypothesis better. However, we still want to do some more work. We want to use a better entity linker, and I want to shamelessly plug the entity linker made by my colleagues, the Rapport entity linker. We want to apply that to this work as well. We want to use other embedding methods because there are many other graph embedding methods next to Wikipedia effect, which we want to try. And we want to use the embeddings in a different manner than we did before. So a different score than the similarity score and the confidence score. And with that, I'd like to conclude my talk. And if you have any questions, you can ask them here. You can send me an email. And if you want to try the code or use the embeddings yourself, you can look them up at our GitHub page. So thank you for listening.
Okay, yeah, thanks. Is there any question? I guess for those who the audience, you want to ask question, you should click the raise hand under the participations page. Is there any questions? I can't see any. So Ima, maybe while we wait, just ask you a quick question.
Yes.
It seems that your accuracy is highly dependent on the matching of query to the correct entities.
Yes.
So I guess it seems that it's best you optimize that. So one question is, if you do a baseline that if you have a perfect match of to entities, what is the performance?
We did not do that, but we want to do that in the future. So we want to manually tag the entities to make sure they're perfectly tagged and then compute the score again. So that's a good question, but we haven't done that yet. So hopefully in the future I can tell you more about that.
Okay, thanks.
That's it. We have hands raised.
Okay, yeah.
So shall I allow to
Can you ask the question?
Jeff Dalton. Hi, Jeff.
Hello. Great work. Very interesting. Well done. Thank you for the presentation. I wanted to go if you could go back to your results for the 5 and FSDM. So you're combining your scores with those results. I think actually one more.
This
yeah.
one?
So I was quite curious here. It looks like there were some major differences across the kind of the kind of relative weights that we have of FSDM versus BM25F.
Yeah.
Indicating there that the FSDM is a lot lower in terms of some of those weights. Did you maybe dig into this a little bit more depth? There's a huge discrepancy between FSDM and BM25F in terms of the relative importance of some of these. And I was just curious what you thought about that.
Yeah, I think it's probably because FSDM also is a more entity-related score, and BM25 is more TF-IDF related score. That's the only thing I can imagine. We did not really investigate that into detail, so I cannot give you a definite answer for that, but it's a good question.
And the related question there was, what was just the FSDM and BM25F scores on their own?
Yeah, I have them here.
Yeah.
So this is just them on their own. Yeah, and then I can show these again. So these, it's a very big table. But you do see an improve in both cases. Yeah.
Okay, thanks. I think we don't have time for question now. Yeah, thanks, Emma, for the presentation.